Now, how do I determine what numbers could be zeros of a polynomial, right? I need a way to narrow it down because otherwise it could be every real number, and that's infinitely many numbers, which is definitely too many numbers. So that's where the rational zeros theorem comes in. So if I have f being a polynomial function of degree 1 or higher of the form that we know polynomials to take, where my ending coefficient isn't 0, if p over q in lowest terms is a rational zero of f, right? So that would mean f of p of q gives us 0. Then p has to be a factor of our a naught, and q must be a factor of an. So let's look at a very familiar example. I have f of x equals x squared minus 5x plus 6, which we know factors to x minus 2, x plus 3, x minus 3. Maybe not that familiar of an example. So that means our zeros, if I have x minus 2 equals 0, I get x is 2, and I have x is 3. Well, 2 and 3, in this case, are factors of 6, right? So p must be our factors of 6, and q is 1. So what are all the factors of 6? Well, I've got 1, 2, plus or minus 2, plus or minus 3, plus or minus 6. And for q, what my divisor is, I only have plus or minus 1. So if I take all the set of p over q, I just get plus or minus 1 because 1 divided by 1 is 1, plus or minus 2 because 2 divided by 1 is 2, plus or minus 3 because 3 divided by 1 is 3, and plus or minus 6. Well, 2 and 3, which are the zeros of the polynomial, are indeed factors of a naught and of the form p over q. So we're going to practice finding all possible rational zeros and then substituting those in to determine which ones are truly zeros. Here in the PowerPoint is a worked through example. So if I have f of x is 3x squared plus 8x minus 7x plus, that's a minus 12, and this should show up better in the PowerPoint you guys were given. Then factors, I'm going to need to take all factors of my constant, which is negative 12, over all factors of my leading coefficient. So that means that my possible p's, which are the factors of 12, are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, and plus or minus 6. Or what are all the factors of q? Well, the factors of 3 are only 1 and itself, as 3 is a prime number. So then what I do is I take all possible fractions. I take 1 over 1, which would give me plus or minus 1, 2 over 1, which would give me plus or minus 2, 3 over 1, which would give me plus or minus 3, 4 over 1, which would give me plus or minus 4, 6 over 1, which would give me plus or minus 6, and 12 over 1, which would give me plus or minus 12. I then have to do the same thing for over 3. I get 1 over 3, which is 1/3, plus or minus 1/3. 2 over 3, which is plus or minus 2/3. 3 over 3, well, that's just 1, and I already have that number represented in my possible rational zeros. Then I have 4 over 3, which would be plus or minus 4/3, 6 over 3, which would be 2, and 12 over 3, which would be 4. So these are all my possible rational zeros. So let's practice listing the potential rational zeros of a couple functions. If I have f of x is 2x cubed plus 11x squared minus 7x minus 6, my possible factors of p, which are all the factors of 6, are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Can you think of any other factors of 6? No, that's it. Then my factors of q, which are of 2, another prime. The only factors of prime numbers are 1 themselves. So I have plus or minus 1 over plus or minus 2. So let's start listing the potential rational zeros. So if I take 1 over 1, that'll give me 1. 2 over 1 is 2, 3 over 1 is 3, and 6 over 1 is 6. Now I have to take all my possible p's over 2. 1 over 2 is 1/2. 2 over 2 is 1, which is already included. 3 over 2 is 3/2. And 6 over 2, well, that's just 3, which is already represented. So here's my list of possible rational zeros, and I did type that up and include that in the PowerPoint so you guys could check your answers as you go along. So how would I find the zeros of f of x is 3x squared plus 8x minus 7x minus 12? So we want to find the real zeros and write this function in factored form. So our step one is we're going to use the degree of the polynomial to determine the maximum number of zeros. This is a degree 3 polynomial, so the maximum number of zeros is 3. Next, if the polynomial has integer coefficients, which it does, use the rational zeros theorem to identify those rational numbers. And we did this about 3 slides ago and found that all the possible rational zeros were plus or minus 1, 2, 3, 4, 6, 12, 1/3, 2/3, and 4/3. Okay? We found all the potential rational zeros. Then use synthetic division or long division to factor the polynomial function, or the fact that f of k is 0 if k is a 0. I think that's faster. Then you will continue to factor your polynomial using knowing how to factor a quadratic, or by having to find more zeros by substituting them in to our function. So I would get f of x is x plus 1, and I have a remainder of 3x squared plus 5x minus 12, and then I'd want to factor this quadratic function. So I finally get that this equals x plus 1 times x plus 3 times 3x minus 4. So I get this, I set this equal to 0. This is my function. So I have x plus 1 times x plus 3 times 3x minus 4. And if I set each of these terms equal to 0, I find that my zeros are x is -1, -3, or positive 4/3. And as you can see, all of these are potential zeros that we could have had. So let's go back to our example that we were doing ourselves, where we have this function f of x here, and we found our potential zeros. Let's start by trying to determine what are the possible zeros of this polynomial. And I like to start at the beginning. Let's start with the easy numbers, right? Like 1. So f of 1 is 2 times 1 cubed plus 11 times 1 squared minus 7 times 1 minus 6, which is 2 plus 11 minus 7 minus 6, which is 13 minus 13, which is 0. Yay! So 1 is a factor. I'm going to go ahead and do the synthetic division to determine my quotient. So I have 2x cubed plus 11x squared minus 7x minus 6. And I pull down this first term. 1 times 2 is 2. 11 and 2 is 13. 1 times 13 is 13. Negative 7 and 13 is 6. 1 times 6 is 6, and my remainder is 0. But we knew that, right? Because f of 1 is 0. So now I have f of x is x minus 1, right? Because it has to be x minus k, times 2x squared plus 13x plus 6. Then I need to go ahead and factor this quadratic. And I could do that by substituting in more possible zeros. That's an option. Or I can find the factors of AC. I gave away the answer, darn it. AC that add up to B. So in this case, AC is 12, because 2 times 6 is 12. But what are some factors of 12 that add up to 13? How about 1 and 12? So I'm going to use factoring by grouping and pull apart this middle term. So I have f of x is x minus 1 times 2x squared plus 12x plus x plus 6. Well, we factor the greatest common factor of 2x squared and 12x is 2x. So I have 2x times x plus 6. The greatest common factor of x and 6 is 1 times x plus 6. So my final polynomial, I'm going to rewrite it in green up here, would be f of x is x minus 1. Collect the greatest common factors, so 2x plus 1 times x plus 6. So I already knew that my zeros are when x equals 1, right? Because x minus 1 is 0, x is 1. Let's determine our other two zeros. So I've got 2x plus 1 is 0. Subtract 1 from both sides. 2x is a negative 1, so x is negative 1/2, which was one of our options. I also have x plus 6, which is set equal to 0, gives us x is negative 6, which was another one of my possible rational zeros. And here's the solution for this. I included it in the PowerPoint, again, so you could check your work. And we could also have found these zeros by graphing. So let's go ahead and do that. Let's go ahead and graph this polynomial in Desmos. So now that we're in Desmos, let's go ahead and graph our polynomial. I had f of x is 2x cubed plus 11x squared minus 7x minus 6. And we had found 3 zeros, and those zeros were negative 6, negative 1/2, and a positive 1. So we could also find rational zeros by graphing.